This is part 3 of block-based digital signal processing. We are just going to go through the Flanger class that I have written and then play a test audio file to see what it sounds like. The Flanger class is based on the echo class that we did in part 2. The equation for the flanger is that the current output is equal to the current input plus a scaled version of the input delayed by an amount d of k. So we have a variable delay. The amount of delay depends on the current sample number. The delay is given by this formula here, which says, well, capital T is 1 on the sample rate. So by using T here, the constants that I set here are going to be independent of the sample rate, so they've got more meaningful units. So I'm going to have a fixed delay and a variable delay. This quantity here sets the largest amount of delay we can get for the variable delay part. And the variable delay is just going to be a sinusoid shifted up by 1. So this term here will be between 0 and 2. And it's essentially just a cosine wave shifted up. And its frequency f is one of the parameters that we can set. So the parameters that we have, we've got the frequency in hertz, the two delays d1 and d2 in milliseconds, the amplitude alpha, and then we need to know the sample rate because the sample rate affects how we scale our coefficients here. We've got the samples per frame for good measure, and we have the number of channels. So unlike the echo that we wrote, this class is going to be able to handle stereo, quadraphonic, etc. It can handle multiple channels. We have got some private variables here that we are going to be using. Buffer is the same as in our echo class. It stores data from the previous block or blocks that we need to be able to access because we're adding a delay, and so sometimes we need to access samples from a previous block, not the current block. Because the delay depends on the time, we need to keep track of time. It's not enough just to know the index into the current block. We need to know the time since the audio track started playing, and that will be held in k offset. And then these three constants are just going to be some calculations. If we go back to the formula here, capital D1 divided by T will be little d1, capital D2 divided by 2T will be D2, and 2 pi ft will be omega. MD stands for max delay. We need to determine what is the largest possible delay value because that's what we have to store in our buffer, data up to that number into the past, max delay into the past. Our basic constructors here, same as before, it allows us to pass parameter values in at the time of constructing the instance of the class. Our setup implementation is now a little bit more complicated because it needs to do some pre-computations. Also, as an improvement to our echo class, here we see that at setup we receive in. Now the way Matlab is set up is that the first time you call the step function for the parent class, it will first of all call setup and reset. And when it calls setup, it will pass exactly the same thing as what was passed to the step function. So remember, the setup function gets called because the user called the step function, and that means that the parameters that the user passes to the step function can also be accessed by setup. That's how Matlab has arranged its code in the parent class. So in other words, when setup is called, in is equal to the very first audio block that we've been given. That means we can have a look at its size and therefore work out the samples per frame and also the number of channels. The rest is just some pre-computation. Remember, our capital T is 1 on the sample rate. Our D1 and D2 are given by these formulae here, as I showed you before. I've divided by 1000 here because I wanted capital D1 and capital D2 to be in milliseconds rather than seconds. I compute the maximum delay by this formula here. Ceiling returns the smallest integer greater than or equal to this number here. So if this were 5.7, then ceiling would return 6. And omega is computed as before too. I like to have it print out the values of these different delays here just to check things are working. You can leave out those display statements if you like. If we just jump down quickly to the reset code, well, the reset code just zeroes our buffer, but this time because we have possibly more than one channel, we actually have to zero an object which stores max delays worth of audio samples per frame, but also we now have to have one column for each channel. So if it's stereo, there'd be 2 columns in our buffer. And the K offset is going to be the K value corresponding to the very start of each block we get. So we start off at 0. We start off at time K equal to 0 here. And then we're almost done. We just have the actual flanging code itself, the step implementation. So we receive an audio block and we must compute an audio block. It's always good to pre-allocate memory for it, so I've just created my output to be the same size as my input. W is the same as in echo, that's my sliding window. The audio data that we have received in the past will be stored in buffer, and the current one is in, and we just put them together. The offset I just assign to a local variable k because it's more convenient to refer to little k than type in obj.k offset everywhere. And then I've got a for loop here. I am expecting, and this is how Matlab expects things to work too, that the size of in is not going to change once you've started. So therefore we know that the number of rows is going to be the samples per frame. So we go through 1 to samples per frame. I calculate my delay for this particular value in time. Now the particular value in time is k, that's its job. So in this loop here, I am computing y of k, if you like, the output at time k. So here is my delay at time k, and it's just the same as my formula before. Here's my k, and my pre-computed constants just mean that I can compute it a bit faster each time through this loop. So D is the current delay. I just have to make sure that the delay is no greater than what's in my buffer and that the delay is not negative. Now, why am I so cautious? Well, just because it reminds me to mention that when you're doing floating point arithmetic, you have to be very careful of rounding errors. So for example, mathematically, we know that 1 minus cos theta can never be less than 0 or greater than 2. When you're working with computers though, they have finite precision. So who knows if 1 minus cos might end up being negative 0.00001, or if 1 minus cos might end up being 2.00001. Now, this is something that when people write their cosine routine and when they write their floating point arithmetic, they actually have to pay a great deal of attention to. So if this really mattered, then we can go to the IEEE standards for floating point arithmetic, etc., and make sure that these things are true. Here, I'm just going to round everything off to the closest integer, and rather than look up all the manuals, etc., I'm just going to put in these assert statements to reassure myself that things are working. Then our output. Now remember, it's block based, so although it's the ith element of the output, that's for this current block. in the scheme of things, this is y of k. So y of k is equal to x of k. How do we get x of k? Well, in our window, so I could have actually written in I here if you prefer, but I just chose to do it this way. We've put in inside our window here. And so to get to in, we have to add the length of our buffer, which is MD. So this is in I. This is our alpha times, and then this is our delayed version. And this is why I wrote this one the way I did. We want to delay it by d units of time, so it's just this index minus d. And because of our window, we know that even if the delayed version doesn't lie in our current input block, it will lie in our buffer. And so this will give us a valid entry into our window here. And once we've done that, then all we do is we add 1 to k and move on and process the next value. And then the last thing we do, we just need to update our buffer and update our k offset. For our buffer, we just keep the last max delay elements of the current window, and we just store our most recent value of k. That will be the time at the start of the next block. The one little thing I haven't mentioned yet is because we're dealing with multiple channels, I use the comma colon in here. All it says is that I'm applying the same operation to each of my columns in here. That allows me to process stereo sound, for example. Now we can go to our test audio. I have downloaded from the internet Toccata and Fugue in D minor. I've got my device writer. Here's my flanger. I've got D1 at 0 milliseconds, D2 at 20 milliseconds, frequency at 0.1 Hertz, and the amplitude at 0.8. Note that I don't have to set my parameters in the constructor here. I can also set parameters, just fl.samplerate equals and give it a number. So I could have done f1.D1 equals to 0, whichever way you prefer. And then while there's still data to read from the file, I grab the next block of audio data, put it through my flanger, and send it to the device writer. Let's see what it sounds like. Definitely some interesting flanging effects in there.